Lesson 1. Overview of the cardiovascular system. Good evening. I am so glad you have chosen to join me here tonight. As the world outside grows quiet and the demands of the day begin to fade into the background, we have a unique opportunity to turn our attention inward. We are going to embark on a journey, not across the globe, but through the vast, intricate, and miraculous landscape of your own body. Finding a comfortable position now, perhaps adjusting your pillow or the blankets, let your body begin to settle. There is no rush here. There is no exam to study for, no test to pass. There is only the gentle rhythm of learning, a story of biology that has been unfolding within you since before you were born. Tonight, we begin a new series, a comprehensive exploration of one of the most vital and elegant systems in human physiology, the cardiovascular system. It is a name you have likely heard 1,000 times, perhaps synonymous in your mind with the heart alone, but as we will discover together, it is so much more than a single organ. It is a masterpiece of engineering, a closed loop of vitality that ensures every microscopic corner of your being receives exactly what it needs, moment by moment, beat by beat. In this first lesson, our goal is simply to see the whole. We want to understand the grand design. Before we inspect the valves or memorize the names of arteries, we must appreciate the philosophy of the system. We want to understand why it exists, how it functions as a unified team, and the history of how we came to understand it. So, take a deep breath, let your shoulders drop, and let us begin our exploration of the rivers of life within you. Let us start with the most fundamental question. What is the cardiovascular system? If we were to strip away the Latin terminology and look at the raw mechanics, we would see that it is, at its core, a transport network. It is the ultimate logistics company, operating 24 hours a day, 7 days a week, with an efficiency that rivals any machine humans have ever invented. In the very simplest of living organisms, like a single-celled amoeba, there is no need for a heart or blood vessels. That tiny creature is in direct contact with its environment. It can simply absorb oxygen and nutrients right through its skin and push waste products out the same way. Diffusion, the natural movement of particles from high concentration to low concentration, is enough. But you are not a single cell. You are a complex galaxy of trillions of cells, many of them buried deep within bone or muscle, far removed from the outside world. Diffusion is too slow for you. You need a highway system. You need a way to bulk transport supplies to the remote villages of your toes and the bustling metropolis of your brain. This is the role of the cardiovascular system. It consists of 3 primary components, which we can think of as the 3 Ps: the pump, the pipes, and the payload, or, in anatomical terms, the heart, the blood vessels, and the blood. First, consider the heart. In our later lessons, we will explore its chambers and valves in great detail, but for tonight, simply visualize it as the engine. It is a muscular pump, roughly the size of your clenched fist, sitting faithfully in the center of your chest. Its primary job is to generate pressure. Fluids, you see, only move if there is a pressure difference flowing from high pressure to low pressure. By contracting rhythmically, the heart creates that high pressure, imparting energy to the blood and driving it forward. It is a double pump, actually. The right side sends blood to the lungs to catch a breath of fresh air, while the left side pushes that refreshed blood out to the rest of the body. Second, we have the blood vessels. These are the pipes, or the vasculature. If the heart is the central station, the vessels are the roads that lead everywhere. They form a closed circuit, meaning the blood ideally never leaves this network. It just cycles round and round. We classify these roads based on the direction of traffic. Arteries are the highways leading away from the heart. They are built to handle the high-speed, high-pressure traffic coming straight from the engine. As they travel further out, they branch into smaller and smaller streets, eventually becoming microscopic lanes called capillaries. The capillaries are where the magic happens. They are the destination. This is where the delivery truck pulls over and unloads. Oxygen and nutrients slip out of the blood and into your tissues, while waste products like carbon dioxide hop on board to be taken away. Once this exchange is done, the vessels merge back together, widening into veins. The veins are the return routes, carrying the blood back to the heart to start the cycle all over again. And finally, the third component is the blood itself. This is the fluid medium, the payload. It is a liquid connective tissue, a river that carries everything necessary for life. It transports oxygen from the lungs, nutrients from the digestive system, hormones from your glands, and heat generated by your muscles. It also acts as a waste removal service, carrying toxins to the liver and kidneys. Without the blood, the heart would be pumping nothing. Without the vessels, the blood would have nowhere to go. Take a moment to let that idea find its place. Visualize these three components working in harmony. The pump creates the push. The pipes guide the flow. The fluid carries the life. It is a seamless, integrated triad, functioning quietly at this very second, ensuring that while you rest, your internal world remains in perfect balance. Now that we have the basic layout, let us deepen our understanding by stepping back in time. It is easy for us, in the modern world, to take this loop concept for granted. We see diagrams of the circulatory system in elementary school textbooks, red lines for arteries, blue lines for veins, connecting in a circle. But for most of human history, this was not the prevailing wisdom. The discovery of the cardiovascular system as we know it is one of the greatest detective stories in the history of science. For over 1,000 years, medicine was dominated by the teachings of the ancient Greek physician Galen. Galen was brilliant, but he had a different theory. He believed that blood was created in the liver from the food we ate. He thought the heart sucked the blood in, like a bellows, and then pushed it out to the body where it was consumed, used up entirely by the organs, much like a fire consumes wood. In this view, blood did not circulate. It was constantly made and constantly destroyed in a one-way street. It ebbed and flowed like the tide, but it did not circle. This view held firm until the early 17th century, when an English physician named William Harvey began to look closer. Harvey was a man of observation and, crucially, a man of mathematics. He began to measure the capacity of the heart. He observed the ventricles, the main pumping chambers, and estimated how much blood they pushed out with each beat. He did a simple calculation, one that changed the world. He reasoned that if the heart pumps roughly 2 ounces of blood per beat, and it beats 72 times per minute, then in a single hour, the heart pumps an enormous amount of blood, far more than the entire weight of the human body. If Galen was right, and the body was consuming the blood, a person would have to eat hundreds of pounds of food every hour just to produce enough blood to keep up. That, of course, was impossible. Therefore, Harvey concluded, the blood must not be consumed. It must be the same fluid, moving in a circle, returning to the heart to be pumped again. He published his findings in 1,628 inches, a book titled De Motu Cordis, on the motion of the heart. He described the heart as a sovereign, the sun of the microcosm of the body, moving the blood in a perpetual circle. This was the birth of modern physiology. It shifted our understanding from a static body to a dynamic one, a system of constant motion and recycling. Let's add some color to this picture by considering the sheer scale of the system Harvey discovered. The anatomy you possess is staggering. If we were to take all the blood vessels in an average adult body, every artery, every vein, and every microscopic capillary, and lay them out end to end in a single line, that line would stretch for approximately 60,000 miles. That is more than twice the circumference of the Earth. Think about that for a moment. Inside your body, right now, is a network intricate and vast enough to wrap around the world twice. And your heart? This tireless pump beats roughly 100,000 times every single day. Over the course of a lifetime, it will beat nearly 3 billion times. It does this without a vacation, without stopping for repairs, and without you ever having to ask it to. It is a testament to the durability and resilience of biology. Furthermore, this system is incredibly adaptive. It is not a rigid set of pipes like the plumbing in your house. It is alive. The vessels can change their size. When you are running, your arteries dilate, they widen to allow more flow to your muscles. When you are cold, the vessels in your skin constrict, they narrow to keep the warm blood deep inside your core. The system is constantly talking to itself, adjusting pressures and flows to meet the exact demands of your current state. Even now, as you lie in bed, your heart rate has slowed and your blood pressure has dipped, shifting into a rest and digest mode to facilitate recovery. If your mind is still following along, try visualizing this. Imagine a map of a great city at night, with millions of roads glowing with light. Some are wide interstates, bright and fast. Some are tiny alleyways, dim and slow. Now imagine that entire map is folded up neatly inside you. It is a bustling world of transport, yet it operates with such silence that you can drift off to sleep right in the middle of it. Why does this matter to us, beyond the academic interest? Why is it helpful to visualize this transport network? Because understanding the cardiovascular system connects us to the very sensation of being alive. Consider the pulse. You have likely felt it many times, perhaps at your wrist, just below the thumb, or at the side of your neck. What you are feeling is not just a flutter under the skin. You are feeling the physical shockwave of the heart's contraction traveling through the fluid of your blood. It is a direct message from the center of your body to the periphery. When a doctor checks your pulse, they are listening to the rhythm of that central engine. A strong, steady pulse tells us that the pump is effective and the pipes are clear. This knowledge also explains so many of our daily experiences. Think about when you are embarrassed and your cheeks turn red. That is the cardiovascular system in action. Your brain signals the blood vessels in your face to dilate, flooding the capillaries near the surface with warm, red blood. Or consider when you are very cold and your fingers turn pale. That is the system prioritizing your survival, constricting the distant vessels to keep the warm blood for your vital organs, the heart and brain. Moreover, the concept of the closed loop helps us understand how our health is interconnected. Because the blood travels everywhere, a problem in one area can affect the whole. A medication you swallow enters the stomach, moves into the bloodstream, and is carried to the headache in your brow or the ache in your knee. The cardiovascular system is the great unifier. It ensures that the lungs, the liver, the kidneys, and the brain are not isolated islands, but partners in a unified continent. This system is also the guardian of homeostasis, the body's ability to maintain a stable internal environment. It balances your pH, regulates your water levels, and distributes immune cells to fight off infections. It is the peacekeeper and the provider. When we look at it this way, we see that the cardiovascular system is not just about plumbing, it is about maintaining the conditions necessary for life itself to flourish. This is a good place to rest your thoughts for a moment before we continue. Let the logic of it wash over you. You are a connected being. Every part of you is in communication with every other part, linked by this silent, flowing river. You are a unified whole. We have now laid the foundation. We have surveyed the landscape and seen the big three, the heart, the vessels, and the blood working in their endless loop. We have honored the history of William Harvey and marveled at the 60,000 miles of pathways within you. But a transport system is defined by what it carries. A highway is only as important as the travelers upon it. So, as we prepare to move forward in our learning journey, we must zoom in. We must take our mental microscope and look at the fluid itself. What is this red liquid that sustains us? What are the tiny cells floating within it, and what are their specific missions? Having grasped the structure of the system, we are perfectly prepared to examine its contents. So, let's hold that thought here. A complete picture of the grand design. Our next lesson will take us into the river itself as we begin our study of blood composition and functions. But for now, let the current carry you gently toward rest. Lesson 2. Blood composition and functions. Welcome back. I hope you are feeling settled and comfortable, ready to continue our quiet exploration of the human body. In our previous session, we stood at a distance, admiring the cardiovascular system as a whole. We looked at the map of the territory, the vast network of 60,000 miles of vessels and the tireless pump that drives them. We established the grand logic of the loop. Now, tonight, we are going to change our perspective. We are going to zoom in. Imagine we are shrinking down, smaller and smaller, until we are standing right at the riverbank of an artery. We are no longer looking at the pipes. We are looking at what flows within them. We are going to study the blood itself. To the naked eye, blood appears simple. If you prick your finger, you see a uniform, bright red droplet. It looks like a single substance, perhaps like red ink or paint. But this is an illusion of scale. If we were to place that single droplet under a microscope, the illusion would vanish, revealing a bustling, crowded world. It is not a simple liquid at all, but a complex suspension, a soup rich with ingredients, each with a specific purpose, each vital to your survival. Tonight, we will separate this mixture. We will identify the liquid carrier and the solid travelers. We will learn why blood is red, how it carries the breath of life, and the silent army it transports to protect you. So, let your breathing slow down to a steady, comfortable rhythm, and let us dive into the stream together. Let us begin with a definition that might sound strange at first. In the language of anatomy, blood is classified as a connective tissue. You might pause at that. We usually think of tissue as something solid, like muscle or bone. How can a liquid be a tissue? It is because, embryologically, it comes from the same origins as your bones and cartilage, and functionally, it connects every part of the body to every other part. It is the only fluid tissue in the human body. To understand what blood is made of, imagine we take a sample and place it in a test tube. If we let it sit, or better yet, if we spin it in a machine called a centrifuge, the components will separate by weight. The heavier elements sink to the bottom, and the lighter fluid floats to the top. What we see in that tube is 3 distinct layers. The top layer, making up about 55% of the total volume, is a pale, straw-colored liquid. This is the plasma. Think of plasma as the riverbed or the broth of the soup. It is the liquid matrix that allows everything else to flow. At the very bottom of the tube is a deep, dense red layer. These are the erythrocytes, or red blood cells. They make up roughly 45% of the blood. This percentage, the volume of red blood cells in your total blood, is a very important number doctors check, called the hematocrit. Sandwiched between the yellow plasma on top and the red cells on the bottom is a very thin, whitish layer comprising less than 1% of the volume. We call this the buffy coat. Despite its small size, this layer is potent. It contains the leukocytes, the white blood cells, and the platelets. So, when you think of blood, think of this triad: the plasma, the fluid, the red cells, the carriers, and the white cells and platelets, the defenders and repair crew. These solid parts, the red cells, white cells, and platelets, are collectively known as the formed elements. We call them formed elements rather than just cells, because, as we will see, some of them are not technically complete cells at all. Let's look first at the plasma. While it is 90% water, it is far from just plain water. It is a solvent of life. Dissolved within this water are over 100 different solutes. It carries nutrients like glucose, amino acids, and vitamins absorbed from your last meal. It carries electrolytes like sodium and potassium, which are the battery acid for your nervous system. It carries respiratory gases, hormones, and waste products. Floating in this plasma are also massive plasma proteins, produced mostly by the liver. The most abundant of these is albumin. You might think of albumin as a water magnet. It stays in the blood and holds onto water, keeping it in the vessels so it doesn't leak out into your tissues. It maintains what we call osmotic pressure. Without enough albumin, the fluid would seep out, and your tissues would swell. Now, let us turn our attention to the star of the show, the erythrocyte, or red blood cell. These are the most abundant cells in your bloodstream. In a single tiny drop of blood, there are millions of them. Their primary job is simple but critical: gas transport. They pick up oxygen from the lungs and ferry it to the tissues, and they pick up some of the carbon dioxide from the tissues and bring it back to the lungs. Finally, we have the leukocytes, or white blood cells. If red blood cells are the cargo ships, white blood cells are the navy. They are the mobile units of the body's defense system. Unlike red blood cells, which stay confined inside the vessels, white blood cells can actually slip out of the bloodstream to hunt down bacteria or viruses in the tissues. And alongside them are the thrombocytes, or platelets. These are not true cells, but merely cell fragments, tiny, jagged pieces of a larger cell. Their job is to stop leaks. They are the emergency repair kits, ready to plug a hole in the vessel wall at a moment's notice. Now that we have introduced the cast of characters, let us spend some time really getting to know them. There is a deep elegance in their design that is worth appreciating. Let's focus deeply on the red blood cell. Its design is a perfect example of form following function. Imagine a round, soft ball of clay. Now, imagine pressing your thumb into the center of the ball and then pressing your finger into the other side, squishing the center until it is thin, but leaving the edges thick. This shape is called a biconcave disc. It looks somewhat like a donut without the hole punched all the way through. Why this specific shape? It serves two brilliant purposes. First, it increases surface area. Just as a radiator has fins to cool down an engine, the indented shape of the red blood cell provides more surface area for oxygen to enter and exit. Second, and perhaps more importantly, it allows flexibility. Some of your capillaries are so narrow that red blood cells have to stack up single file to get through. This flexible, squishy shape allows them to bend, fold, and twist as they navigate the tightest corners of your circulatory system, only to spring back into shape when the vessel widens. But the red blood cell makes an even greater sacrifice for efficiency. When a red blood cell is born in the bone marrow, it has a nucleus and organelles, just like any other cell. But as it matures and prepares to enter the bloodstream, it ejects its nucleus. It literally throws away its own brain and its ability to divide or repair itself. Why would a cell do this? To make room. By getting rid of the nucleus, the cell becomes a simple sac designed to hold as much hemoglobin as possible. Hemoglobin is the protein that actually binds to the oxygen. It is a pigment that gives blood its red color. At the center of each hemoglobin molecule is an atom of iron. It is this iron that acts as a magnet for oxygen. Take a moment to let that idea find its place. Consider that the iron in your blood, the very element that allows you to breathe, was forged in the heart of a dying star billions of years ago. You carry the history of the universe in every red blood cell. Because they lack a nucleus, red blood cells cannot repair themselves. As they travel through the rough and tumble of the circulatory system, bumping into walls and squeezing through capillaries, they wear out. They live for about 120 days, roughly 4 months. After this tour of duty, they become stiff and fragile. As they pass through the spleen, often called the red blood cell graveyard, they are trapped and broken down. But the body is thrifty. It recycles the iron to make new cells. Let us briefly touch on the white blood cells again. While we won't list every type tonight, know that they are the only complete cells in the blood, possessing nuclei and organelles. They are far fewer in number than red cells. For every one white blood cell, there are nearly 1,000 red ones. Yet, during an infection, their numbers can double within hours. This is why doctors check your white blood cell count to see if you are sick. A high count means the army has been mobilized. And finally, the platelets. These are fascinating because of their origin. They come from a giant cell in the bone marrow called a megakaryocyte. This giant cell presses up against a blood vessel and literally sheds pieces of itself into the stream, like leaves falling from a tree. These fragments are the platelets. They are inactive as they float around, but the moment they encounter a damaged vessel, they swell, grow spikes, and become sticky. They transform from passive drifters into active construction workers. How does this microscopic knowledge connect to your daily life? How does the composition of this fluid affect how you feel? Consider the concept of viscosity. Viscosity is the thickness or stickiness of a fluid. Water has low viscosity. Honey has high viscosity. Blood is about 5 times more viscous than water. This thickness creates resistance, which is important for maintaining blood pressure. However, this balance is delicate. Remember the plasma, the water-based broth? If you become dehydrated, you lose water from the plasma, but the number of red blood cells stays the same. This means the blood becomes thicker, more like a sludge than a river. The heart, your faithful pump, has to work much harder to push this thick fluid through the pipes. This is one of the primary reasons why hydration is so critical for your energy levels and heart health. By drinking water, you are literally thinning the river, easing the burden on your heart, and allowing oxygen to flow more freely to your brain. We can also understand conditions like anemia through this lens. Anemia simply means the blood's ability to carry oxygen is reduced. This could be because you don't have enough red blood cells, or perhaps because you don't have enough iron to build the hemoglobin. The result is fatigue. Without the cargo carriers, the tissues starve for oxygen, and you feel tired and weak, no matter how much you sleep. It is a logistics failure. Another fascinating connection is the color of blood. We often hear that blood inside the body is blue, but this is a myth. Blood is always red. When hemoglobin is fully loaded with oxygen, it is a bright, vibrant scarlet. This is the blood in your arteries. When it has delivered its oxygen and is returning to the heart through the veins, it turns a dark, deep crimson. It looks blue through your skin only because of how light scatters through the layers of tissue and the vessel walls. But inside, the river is always red. Don't worry about memorizing the details. Just let the logic of it wash over you. Think of the red blood cells as millions of tiny rafts floating down a stream. They are loaded with supplies, navigating the bends and turns, delivering life to the shores, and then drifting back to be reloaded. It is a cycle of giving and receiving that happens without you lifting a finger. We have now defined the fluid. We know it is a mixture of plasma and formed elements. We have met the red cells that carry our breath, the white cells that guard our borders, and the platelets that wait for emergency. We understand that this fluid must flow freely, with just the right thickness, to sustain us. But what happens if the pipe breaks? What happens if this precious fluid is threatened by a cut or a tear? The system cannot afford to lose its volume. It must have a way to seal the breach, and it must do so instantly. This leads us to one of the most miraculous and complex cascades in human physiology, the process of hemostasis. It is the body's self-sealing technology. So, let us hold that thought here, visualizing the busy, flowing river of cells we have just studied. In our next lesson, we will watch what happens when that flow is interrupted and how the body builds a dam to save itself. Rest your mind on the image of the steady stream, and when we return, we will explore the art of the clot. Lesson 3. Hemostasis and Coagulation. Welcome back to our sanctuary of learning. It is good to have you here again. As the quiet of the night deepens around you, allow yourself to sink further into that space of relaxation you have created. Let the tensions of the day unravel, thread by thread, until all that remains is the steady rhythm of your breathing and the sound of my voice guiding you inward. In our last session, we spent our time among the currents. We visualized the blood as a busy, life-sustaining river, teeming with red carriers, white defenders, and tiny platelet fragments. We marveled at the composition of this fluid that flows through 60,000 miles of vessels within you. It is a beautiful image, a continuous, unobstructed flow. But, as with any complex system, we must ask the difficult question: what happens when things go wrong? What happens when the pipes burst? The cardiovascular system is a pressurized loop. If a vessel is cut or torn, the integrity of the entire system is threatened. In a pressurized system, a leak is not just an inconvenience, it is a crisis. If the leak is not sealed, the pressure drops, the flow stops, and the life-sustaining delivery of oxygen ceases. Tonight, we are going to explore the miracle of repair. We are going to study the body's emergency response system. It is a process that happens automatically, often without you even noticing. Yet it involves a sequence of events so precise and so chemically complex that it rivals the operations of a nuclear power plant. This process is called hemostasis. The word comes from the Greek roots hemo, meaning blood, and stasis, meaning standing still. Literally, it is the art of making the blood stand still. It is the mechanism by which your body builds a dam against the flood. Tonight, we will watch this process unfold step by step, from the first moment of injury to the final weaving of the safety net. So, settle in and let us observe the wisdom of your own healing. To understand hemostasis, we must first set the stage. Imagine a healthy blood vessel as a smooth, well-paved tunnel. The inner lining, called the endothelium, is slick like a non-stick pan. This smoothness prevents the blood cells from sticking as they rush by. But the moment that lining is broken, perhaps by a tiny cut on your finger or a bump on your knee, the underlying tissue is exposed. This exposure is the alarm bell. It triggers a fast-acting, three-step sequence. The first step is immediate and mechanical. It is called vascular spasm. Imagine you are watering your garden with a hose, and suddenly the hose springs a leak. Your first instinct is to grab the hose and pinch it tight, kinking it to stop the flow. Your body does exactly the same thing. The smooth muscle in the wall of the damaged blood vessel contracts violently. It squeezes the vessel shut, narrowing the diameter. This effectively pinches the hose. By reducing the size of the opening, the body drastically slows the loss of blood. It is a crude, brute force solution, but it buys precious time, usually about 20 to 30 minutes, for the more delicate repair work to begin. While the vessel is clamping down, the second step begins. This is the formation of the platelet plug. Recall from our last lesson that platelets are those tiny cell fragments floating in the plasma. Normally, they are smooth and passive, drifting along like fallen leaves in a stream. But when the vessel lining is broken, the collagen fibers underneath are exposed. Collagen is rough. When platelets touch these rough fibers, they undergo a startling transformation. They stop being smooth. They swell up and grow spiky extensions, looking somewhat like a burr or a sea urchin. They become incredibly sticky. They adhere to the exposed collagen, anchoring themselves to the site of the injury. But they don't just stick to the wall. They stick to each other. As they pile up, they release chemical messengers, signals that scream into the bloodstream. Emergency. We need help here. These chemicals attract even more platelets from the passing blood. It is a positive feedback loop. The more platelets that gather, the more chemicals they release, and the more platelets arrive. Within moments, they pile up to form a loose, temporary plug. Think of this like stacking sandbags against a flood. It is effective for small breaks, but it is not permanent. It is fragile. If the pressure rises too high, the plug could wash away. This brings us to the third and most complex step, coagulation, or blood clotting. This is where the liquid blood transforms into a solid gel. If the platelet plug is a stack of loose bricks, coagulation is the mortar that cements them together. It turns the fragile plug into a sturdy, waterproof seal. This process relies on a protein called fibrin. Normally, fibrin exists in your blood in a dissolved, liquid form called fibrinogen. It is invisible, floating harmlessly in the plasma. But during coagulation, a chemical change occurs that turns liquid fibrinogen into solid fibrin threads. These threads are like spider silk, incredibly strong and insoluble. They weave themselves through and around the platelet plug. They form a dense mesh, a microscopic net that traps red blood cells and platelets, locking them in place. What was once a loose pile of cells becomes a solid mass. The liquid has become a solid. The bleeding stops. The vessel is sealed. Take a moment to let that idea find its place. Visualize that tiny net being woven. Thread by thread, it captures the flow, turning a chaotic leak into a calm stillness. It is order emerging from disorder. Now that we have the three basic steps, the spasm, the plug, and the clot, let us dive deeper into the chemistry of that third step, coagulation. This is often where students of anatomy feel overwhelmed, but we will walk through it gently. Coagulation is not a single reaction, it is a cascade. Imagine a long line of dominoes standing on end. You cannot knock over the last domino by itself. You must push the first one, which hits the second, which hits the third, and so on. In the blood, these dominoes are called clotting factors. Most of these clotting factors are proteins produced by your liver. They circulate in your blood in an inactive form, waiting for the signal. We number them with Roman numerals factor I, factor 2, factor X, and so on. The cascade can be started in two ways. There is the extrinsic pathway, which is triggered by damage to the tissue outside the vessel, like when you cut your skin. It is fast and explosive. Then there is the intrinsic pathway, which is triggered by damage inside the vessel, like the roughening of the vessel wall due to plaque. This pathway is slower and more complex. But regardless of how it starts, both pathways meet at a common point, factor X, 10. Once factor X is tipped over, the race to the finish line is on. Factor X activates an enzyme called thrombin, and thrombin is the master builder. It is thrombin that takes the liquid fibrinogen and snips it into the solid fibrin threads. Why is this system so complicated? Why so many steps? Why not just have the blood clot instantly? The answer is safety. Because clotting is so powerful, it turns your life-sustaining fluid into a solid. It is also dangerous. If blood clotted when it wasn't supposed to, it would block your vessels, causing a heart attack or a stroke. The cascade acts as a fail-safe mechanism. It requires multiple keys to be turned in a specific order to unlock the clot. It ensures that clotting only happens when there is genuine damage. It is a biological safety lock. We must also give credit to the silent partners in this process. One is vitamin K. Without vitamin K, the liver cannot produce 4 of the essential clotting factors. This is why a simple vitamin deficiency can lead to uncontrolled bleeding. It reminds us again that the cardiovascular system is dependent on what we consume. Another partner is calcium. We usually think of calcium as the stuff of bones and teeth, but it is also a crucial cofactor in the clotting cascade. Without calcium ions present in the blood, the dominoes cannot fall. But the story doesn't end when the clot is formed. If the clot stayed there forever, it would eventually block the healed vessel. So, the body has a cleanup crew. This process is called fibrinolysis, the breaking of the fiber. As the vessel wall heals, the endothelial cells release a clot-busting enzyme called plasmin. Plasmin is like a pair of molecular scissors. It slowly snips away the fibrin threads, dissolving the clot bit by bit. It is a slow, controlled demolition. By the time the tissue underneath is fully repaired, the clot has dissolved and washed away, leaving the vessel smooth and open once again. If your mind is still following along, try visualizing this. Imagine a construction crew building a scaffolding to repair a bridge. They build it strong and fast. They do the repair work behind the safety of the scaffold. And when the bridge is fixed, they dismantle the scaffolding piece by piece, leaving no trace that they were ever there. That is the elegance of fibrinolysis. How does this intricate chemical dance manifest in your waking life? You have seen the results of hemostasis hundreds of times, likely without realizing what you were looking at. The most common example is the scab. When you scrape your knee, the blood clots on the surface of the skin. As the clot dries out and oxidizes, it hardens into a crust. This is the scab. It is not dead tissue to be picked away. It is a biological bandage. It is the fibrin mesh and the trapped platelets, forming a shield to protect the delicate healing taking place underneath. When the scab falls off naturally, it means the repair is complete and the scaffolding is no longer needed. We also see this process in the phenomenon of a bruise. If you bump your arm against a table, you might not break the skin, but you crush the small capillaries underneath. Blood leaks out into the surrounding tissue. Hemostasis kicks in to stop the leak, but the blood is trapped there. At first, the bruise is reddish-blue, the color of the deoxygenated blood. Over a few days, it turns green, then yellow. This changing rainbow is the result of your immune system cleaning up the mess. It is breaking down the hemoglobin from the spilled red blood cells and recycling the iron. The colors are the chemical byproducts of that recycling process. It is a visible sign of your body's housekeeping services in action. However, we also see what happens when this system is out of balance. If the blood clots too easily, we get a thrombus, a clot that forms in an unbroken vessel. If this clot breaks free and travels, it becomes an embolus, which can lodge in the lungs or brain. This is why patients at risk are often given blood thinners. Interestingly, many blood thinners, like aspirin, work by making the platelets less sticky, preventing that second step of the process. Others, like warfarin, work by interfering with vitamin K, stopping the liver from making the dominoes. On the other hand, if the blood does not clot enough, we have conditions like hemophilia. In these individuals, one of the dominoes in the cascade is missing, usually factor VIII or IX. The sequence breaks. The plug forms, but the cement never hardens. Even a small cut can be dangerous. It highlights just how vital this cascade is to our daily survival. But for you, resting here tonight, the system is in perfect equilibrium. Your blood flows freely where it should, and yet the potential to stop that flow is always there, waiting in the background, ready to spring into action within seconds if needed. It is a silent guardian, a watchman that never sleeps so that you can. This is a good place to rest your thoughts for a moment before we continue. Let the complexity of the chemistry fade. What remains is the feeling of safety. You are self-repairing. You are resilient. Your body knows how to heal itself. We have now explored the fluid and the safety mechanisms that keep it contained. We have seen the blood as a transporter and as a self-sealing substance. We have understood the what and the how of the liquid medium. But a fluid, no matter how miraculous, cannot move itself. It requires a force. It requires a driver. The pipes and the blood are static without the engine that powers the entire loop. It is time to turn our attention to the center of the chest. It is time to visit the powerhouse. In our next lesson, we will open the doors to the most famous muscle in the human body. We will walk through its chambers, inspect its valves, and understand the anatomy of the heart itself. So, let the image of the healing net fade gently from your mind. Prepare yourself to approach the rhythm that has been with you since the very beginning. When we return, we will enter the anatomy of the heart. Lesson 4. Anatomy of the heart. Welcome back. As we settle into our fourth session together, I invite you to bring your awareness to the center of your chest. There, beneath the sternum, slightly to the left, beats the rhythm of your life. It has been there since you were a tiny cluster of cells, long before you took your first breath, and it will be there until the very end. Tonight, we are going to visit this faithful companion. We are going to explore the anatomy of the heart. In our previous lessons, we spoke of the system in broad strokes. We spoke of the 60,000 miles of vessels and the complex fluid that travels through them. We discussed the chemistry of clotting and the physics of transport. But all of that, the vessels, the blood, the clotting factors, would be motionless and silent without the engine that drives it. The heart is often spoken of in poetry and song as the seat of emotion, the home of the soul, or the keeper of secrets. While we will treat it tonight as a biological structure, we cannot help but respect the reverence humanity has held for this organ throughout history. It is the core. It is the hub. Physically, it is roughly the size of your clenched fist, a hollow, muscular cone weighing less than a pound. It rests snugly in a space between the lungs called the mediastinum. It is protected by the cage of your ribs and cushioned by the soft tissue of the lungs. Tonight, we will gently open the doors of this house. We will walk through its rooms, inspect its walls, and examine the delicate doors that keep the traffic flowing. We will move beyond the simple idea of a pump and see the intricate architecture of the heart for what it truly is, a masterpiece of biological engineering. So, breathe deeply and let us enter the chamber. To understand the heart, we must first understand its basic layout. Imagine the heart not as a single solid block, but as a house with 4 distinct rooms. There are 2 rooms upstairs and 2 rooms downstairs. The 2 upper rooms are called the atria, the singular is atrium. The word comes from the Latin for entryway or hall. In Roman architecture, the atrium was the central court where guests were received. In your heart, the function is exactly the same. The atria are the receiving chambers. They collect the blood returning from its journey either from the body or from the lungs. Because their job is mostly just to receive and hold blood before passing it downstairs, their walls are relatively thin. They do not need to push hard. They simply need to welcome the flow. The 2 lower rooms are called the ventricles. This word comes from the Latin for little belly. These are the pumping chambers. They are the powerhouses. When they contract, they eject blood out of the heart and into the great arteries. Because they have to push blood against gravity and friction to the furthest reaches of your body, their walls are thick, muscular, and strong. So, we have a 4-chambered box: right atrium, right ventricle, left atrium, left ventricle. But a house is not functional without doors. If the rooms were just open to each other, blood would slosh back and forth aimlessly. To create a directed flow, the heart possesses 4 one-way valves. These valves are flaps of connective tissue that open to let blood through and slam shut to prevent it from going backward. Let us trace the path through these doors. Between the upstairs atria and the downstairs ventricles lie the atrioventricular valves, or AV valves for short. On the right side of the heart, between the right atrium and right ventricle, sits the tricuspid valve. As the name suggests, it has 3 little flaps, or leaflets. Think of it as a gate with 3 parts that meet in the middle. On the left side, between the left atrium and left ventricle, sits the mitral valve. This valve has only 2 flaps. It is named after the mitre, the tall 2-pointed hat worn by bishops, because of its resemblance to that shape. It is also sometimes called the bicuspid valve. These 2 valves, the tricuspid and the mitral, are the inlet doors to the ventricles. When the heart relaxes, they hang open, allowing blood to pour downstairs. When the ventricles contract, the pressure forces them to slam shut, sealing the room so blood can only go one way, out. But where does the blood go when it leaves the ventricles? It passes through the second set of doors, the semilunar valves. These are named for the crescent moon shape of their leaflets. The pulmonary valve guards the exit of the right ventricle, leading to the lungs. The aortic valve guards the exit of the left ventricle, leading to the massive aorta and the rest of the body. Unlike the floppy AV valves, these exit doors are stiffer. They are pushed open by the force of the blood rushing out, and then they snap shut as soon as the flow tries to reverse. Take a moment to let that idea find its place. Visualize the rhythm. The top doors open, the bottom doors close. The bottom doors open, the top doors close. It is a synchronized dance of gates, ensuring that the river of life only ever flows forward, never backward. Now that we have the blueprint of the rooms and doors, let us look at the materials used to build this house. The heart is not just a uniform lump of meat. It is composed of 3 distinct layers of tissue, each with a specific function. The innermost layer, the one that actually touches the blood, is called the endocardium. This is a sheet of white, glistening endothelium. It is incredibly smooth, slick, like wet ice. This smoothness is critical. As we learned in our previous lesson, if blood touches a rough surface, it clots. The endocardium ensures that the blood glides through the chambers without friction or turbulence, preventing dangerous clots from forming inside the pump itself. The middle layer is the massive muscular wall, the myocardium. This is the part that does the work. It consists of cardiac muscle cells arranged in spiral bundles. When these bundles contract, they don't just squeeze the heart like a fist, they wring it out, like twisting a wet towel. This twisting motion is far more efficient at ejecting blood than a simple squeeze would be. The outermost layer is the epicardium, which is actually part of a larger sac called the pericardium. Imagine placing your fist into a partially inflated balloon. The balloon wraps around your fist. This double-walled sac surrounds the heart. Between the layers is a tiny amount of pericardial fluid, which acts as a lubricant. This allows the heart to beat friction-free within your chest. Without this slick sac, the heart would rub raw against your lungs and ribs with every beat. Let us return to the chambers for a moment to appreciate a crucial detail of asymmetry. If you were to slice a heart open, you would notice something striking immediately. The left ventricle is vastly thicker than the right ventricle. The wall of the left ventricle is a thick, meaty chunk of muscle, while the right is much thinner. Why this difference? It is a perfect example of physiology dictating anatomy. The right ventricle only has to pump blood to the lungs, which are right next door. It is a low-pressure, short-distance trip. It doesn't need much muscle power. The left ventricle, however, has a monumental task. It must pump blood to the top of your head against gravity, and all the way down to your toes through thousands of miles of resistance. It has to generate 5 to 7 times as much pressure as the right side. So, like a weightlifter who specializes in a heavy lift, the left ventricle has built up massive muscle mass. It is the heavy lifter of the cardiovascular system. We should also pay respect to the skeleton of the heart. We rarely think of the heart as having a skeleton, but it does. It is not made of bone, but of dense, fibrous connective tissue. This fibrous skeleton forms rings around the 4 valves, giving them a sturdy frame to anchor to. It also serves as an electrical insulator, separating the atria from the ventricles electrically, a detail that will become very important when we discuss how the heart beats in a future lesson. Finally, consider the blood supply to the heart itself. It is a cruel irony that the heart is filled with blood, yet it cannot extract any oxygen or nutrients from the blood inside its chambers. The walls are too thick. Instead, the heart has its own private set of vessels, the coronary arteries. These arteries branch off from the very base of the aorta, catching the freshest, most oxygen-rich blood the moment it leaves the heart. They wrap around the outside of the heart like a crown, hence the name coronary. If these arteries become blocked, the muscle starves, leading to a heart attack. It reminds us that even the provider needs provision. Even the caretaker must be taken care of. If your mind is still following along, try visualizing this. See the heart as a self-sustaining island. It pumps for the world, but it also draws from the stream for itself, a continuous loop of giving and receiving. How does this anatomical tour connect to your everyday experience? The most common connection is sound. We have all heard the classic sound of the heartbeat, lub-dub, lub-dub. But what are we actually hearing? We are not hearing the muscle contract. Muscle contraction is silent. What we are hearing is the slamming shut of the doors. The first sound, the lub, is the sound of the tricuspid and mitral valves closing. This happens when the ventricles start to squeeze. The pressure rises, forcing the intake doors to snap shut to prevent backflow into the atria. It is a long, booming, resonant sound. The second sound, the dub, is the sound of the pulmonary and aortic valves closing. This happens when the squeeze is finished and the ventricles relax. The blood in the arteries tries to fall back into the heart, but it catches in the pockets of the semilunar valves, snapping them shut. This sound is sharper and shorter. So, lub-dub is essentially doors shut, doors shut, doors shut, doors shut. Doctors use a stethoscope to listen to these sounds because they tell a story about the health of the valves. If a valve is stiff and doesn't open fully, the blood whistles as it is forced through a narrow opening. If a valve is floppy and doesn't close tight, the blood swishes back through the gap. These abnormal sounds are called heart murmurs. A murmur is simply the sound of turbulence. It is the wind whistling through a crack in the window. Furthermore, understanding the anatomy explains the logic of left-sided versus right-sided heart issues. If the left side of the heart is weakened, perhaps by years of high blood pressure, it cannot pump effectively. The blood backs up behind it. Where does it back up to? Into the lungs. This causes fluid in the lungs, shortness of breath, and coughing. Conversely, if the right side is weak, the blood backs up into the body. This leads to swelling in the ankles, the legs, and the abdomen. The symptoms you see on the outside are a direct result of the plumbing problems on the inside. This is a good place to rest your thoughts for a moment before we continue. You don't need to analyze the sounds. Just know that the rhythm in your chest is the sound of perfect mechanical timing. It is the sound of doors opening and closing, millions of times a year, keeping the currents flowing in the right direction. We have now constructed the heart in our minds. We see the 4 chambers, the receiving atria, and the pumping ventricles. We see the four valves, the guardians of direction. We see the layers of the wall and the protective sac that holds it all. We have a complete engine, but an engine is useless without a destination. We know the blood leaves the ventricles, but where exactly does it go? We touched on it briefly, the lungs and the body, but the specific routes are fascinating in their own right. There are two great loops of circulation. One is a short, restorative trip to gather air. The other is a long, arduous journey to feed the world of your body. These are the pulmonary and systemic circuits. Having grasped the structure of the house, we are perfectly prepared to step out the front door and follow the path of the traveler. So, let's hold that thought here, a complete piece of the puzzle, the anatomical heart. Our next lesson will hand us the adjacent piece, which is the map of the journey itself. For now, let the image of the beating heart gently fade, leaving only the comfort of its rhythm to rock you towards sleep. Lesson 5. Pulmonary and Systemic Circulation. Welcome back. I am glad you have returned to continue this journey with me. In our last session, we constructed the heart. We stood within its chambers, admiring the thick muscular walls of the ventricles and the delicate, swaying leaflets of the valves. We built the engine of life in our minds, a four-chambered masterpiece resting in the center of your chest. But an engine, no matter how perfectly designed, does not exist for its own sake. It exists to create movement. It exists to push a vessel to a destination. Tonight, we are going to leave the engine room and become travelers. We are going to follow the path of a single drop of blood as it navigates the vast, winding highways of the body. You might think of the circulatory system as a simple circle, a single loop, like a racetrack. But the reality is far more elegant. You possess a double circulation system. Imagine a figure 8, with the heart sitting at the crossover point in the center. One loop of the 8 is small and delicate. The other is large and expansive. Tonight, we will travel both of these loops. We will take the short, restorative trip to the lungs, known as the pulmonary circuit, and we will take the long, demanding journey to the far reaches of the body, known as the systemic circuit. These two trips happen simultaneously, beat after beat, in a perfect rhythm of departure and return. So, settle yourself comfortably. Let your breathing become slow and regular, mimicking the steady flow we are about to describe. Imagine yourself small and weightless, ready to drift along the currents of your own biology. Let us begin our journey at the end of the line, which is also the beginning. Imagine we are tracking a single red blood cell. Let's call him Traveler. Traveler has just finished a long trip around your body. He is tired. He has given away all his oxygen to your muscles and brain. He is carrying a load of carbon dioxide waste. He is essentially empty of life force. Because he is depleted of oxygen, he is a dark, deep crimson color, almost purple. In medical diagrams, we always paint him blue at this stage to signify his deoxygenated state. The pulmonary circuit, the short loop. Traveler arrives at the heart through the great veins, entering the right atrium. This is the waiting room for the tired blood. When the atrium contracts, Traveler is pushed through the tricuspid valve and down into the right ventricle. Now, the journey begins. The right ventricle contracts. Traveler is ejected out through the pulmonary valve and into a massive vessel called the pulmonary trunk. This trunk splits immediately into two arteries, one for the left lung, one for the right. Notice something important here. The right side of the heart is not pumping very hard. It doesn't need to. The lungs are right next door. If the right ventricle pumped with the same explosive force as the left, it would damage the delicate tissues of the lungs. So, this is a low-pressure trip. Traveler flows into the lungs. The arteries branch into smaller and smaller arterioles. and finally into billions of microscopic capillaries that wrap around the tiny air sacs of the lungs, called alveoli. Here, a magical exchange happens. It is the reason you are breathing right now. The carbon dioxide that Traveler has been carrying slips off his back and diffuses into the air sac to be exhaled. Simultaneously, fresh oxygen from the air you just breathed in rushes across the membrane and binds to Traveler's iron core. In an instant, he transforms. He changes from that dark, dull crimson to a brilliant, vibrant scarlet. He is recharged. He is oxygenated. Now, he must return to the hub. He flows out of the lung capillaries, into larger venules, and finally into the pulmonary veins. These veins lead him straight back into the left atrium of the heart. This entire trip from the right side of the heart to the lungs and back to the left side is the pulmonary circuit. Its sole purpose is gas exchange. It is the refueling run, the systemic circuit, the long loop. Traveler is now sitting in the left atrium, bright, red, and full of energy. He passes down through the mitral valve into the left ventricle. This is the main launch pad. The left ventricle squeezes with immense power. Traveler is blasted out through the aortic valve and into the aorta. The aorta is the largest artery in the body, the superhighway of the systemic circuit. From here, the road diverges into 1,000 paths. Some blood shoots upward into the carotid arteries to feed the brain. Some flows into the coronary arteries to feed the heart itself. The rest travels down the descending aorta, which runs like a pipeline down the center of your torso. As the aorta descends, it sends off branches like exits on a freeway. There is an exit for the stomach and intestines, an exit for the kidneys, an exit for the liver. Finally, at the hips, the road splits to go down each leg. Traveler flows down these arteries, into the arterioles, and finally into the systemic capillaries. This is the destination. This is where the work gets done. Let's say Traveler ends up in a muscle cell in your calf. The muscle is working and needs fuel. Traveler releases his oxygen, which diffuses into the muscle cell. In exchange, the muscle cell hands him its waste carbon dioxide. The transaction is complete. Traveler is now deoxygenated again. He turns dark red. He leaves the capillary and enters the venules, which merge into larger and larger veins. Gravity might be against him now, but the veins have one-way valves to help him climb back up the leg. Eventually, all the veins from the lower body merge into a massive vessel called the inferior vena cava. All the veins from the head and arms merge into the superior vena cava. Both of these great veins dump their contents into the right atrium, bringing Traveler back to exactly where he started. The loop is closed. The systemic circuit from the left heart to the body and back to the right heart is complete. Now that we have traced the map, let us deepen our understanding by asking, why? Why is it arranged this way? Why the figure 8? If we look at the animal kingdom, we see that not everyone has this luxury. A fish, for example, has a simple two-chambered heart and a single loop. The heart pumps blood to the gills to get oxygen, and then that same blood continues directly to the body. The problem with the fish's system is pressure. When blood passes through the tiny capillaries of the gills, it encounters friction and loses almost all its pressure. It trickles out the other side. This means the flow to the rest of the fish's body is slow and sluggish. This is fine for a cold-blooded fish floating in water, but it would be disastrous for you. You are a warm-blooded mammal. You have a high metabolism. You need to generate heat. Your brain is a supercomputer that demands a constant, high-speed torrent of oxygen. A sluggish flow would not sustain you. The evolution of the double pump or the figure-8 loop solved this problem. By bringing the blood back to the heart after the lungs, we get a chance to repressurize it. Think of it like a pit stop in a race. The blood goes to the lungs. Pit stop 1 gets new tires and fuel, but it loses speed. Instead of trying to finish the race at that slow speed, it comes back to the garage, the heart. The left ventricle then hits the gas pedal again, sending the blood out to the body at maximum velocity. This reboost allows us to be active, thinking, warm creatures. Let us also clarify a point of confusion that trips up almost every anatomy student. It is the paradox of color. We are taught early on, arteries are red, veins are blue. Arteries carry oxygen, veins carry waste. This is true for the systemic circuit, the body loop, but in the pulmonary circuit, the lung loop, everything is reversed. The pulmonary artery carries blood away from the heart to the lungs. Therefore, by definition, it is an artery. But what is it carrying? It is carrying the tired, deoxygenated blood. So, it is a blue artery. The pulmonary veins carry blood back to the heart from the lungs. Therefore, by definition, they are veins. But what are they carrying? Fresh, oxygenated blood. So, they are red veins. Take a moment to let that idea find its place. Do not rely on the color, rely on the direction. Artery means away. Vein means visit, return. The plumbing is defined by the road it travels, not the cargo it carries. There is one more special detour we should mention, the hepatic portal system. Usually, blood goes heart, is greater than artery, is greater than capillary, is greater than vein, is greater than heart. But the digestive system is special. Blood leaves the stomach and intestines full of nutrients from your food. But it is also full of potential toxins you might have eaten. We don't want to send that straight to the heart and brain. So, instead of going home, this blood takes a detour. It goes from the capillaries of the stomach into a vein that leads directly to the liver. The liver inspects the blood, filters out the toxins, and processes the nutrients. Only then does it allow the blood to re-enter the main circulation. It is a security checkpoint before the cargo is released to the general public. How does this knowledge of the two loops help us understand our own health? It clarifies the mechanics of heart failure, a term that often sounds vague but is mechanically precise. Because the loops are separate, they can fail separately. Imagine a traffic jam. If there is an accident on the highway, traffic backs up behind the accident. If the left ventricle, the systemic pump, becomes weak, perhaps from high blood pressure, it cannot pump out all the blood it receives. The traffic jam happens behind it. Where is behind the left ventricle? The lungs. Blood backs up into the pulmonary circuit. The pressure rises in the lung capillaries, and fluid leaks out into the air sacs. This is why people with left-sided heart failure have shortness of breath. They are literally drowning in their own fluid because the pump can't clear the return line from the lungs. Conversely, if the right ventricle, the pulmonary pump, is weak, perhaps due to lung disease, it cannot push blood into the lungs. The traffic backs up behind it. Where is behind the right ventricle? The body. The systemic veins become congested. Fluid leaks out into the tissues of the legs, the ankles, and the abdomen. This is why swollen ankles can be a sign of heart trouble. So, when a doctor listens to your lungs or checks your ankles for swelling, they are acting as a mechanic checking the pressure in the two different loops. They are determining which side of the figure eight is clogged. If your mind is still following along, try visualizing this. Picture two circles of light, one small and one large, intersecting at your chest. They pulse in unison. The light flows round and round, a perpetual motion machine that has been running since before your birth. It is a river that flows into itself, endless and unbroken. Also, consider the sheer velocity of this system. It takes about 1 minute for a single drop of blood to complete the entire circuit, to go to the lungs, come back, go to the toe, and come back. When you exercise, it can happen in as little as 20 seconds. Your blood is rushing through you at a pace that defies the stillness you feel while resting. We have now traced the path. We know the roads. We know the difference between the restorative trip to the lungs and the delivery trip to the body. We understand why the heart is a double pump and how this design grants us the energy to be human. But there is a question we have not yet answered. We know the heart pumps. We know the valves open and close. But what tells it to do so? The heart does not wait for a command from the brain for every single beat. If it did, you would have to think about your heartbeat. You would have to concentrate to stay alive. Instead, the heart possesses a secret. It has its own internal spark. It has a hidden wiring system, a network of electrical nodes that generate a rhythmic pulse all on their own. This is the cardiac conduction system. Having grasped the mechanical plumbing, we are perfectly prepared to study the electrical wiring. So, let's hold that thought here, the image of the flowing loops. Our next lesson will introduce us to the spark that sets the whole system in motion. For now, simply drift in the knowledge that the flow continues, silent and sure, carrying you gently into the night. Lesson 6. The Cardiac Conduction System. Welcome back. I hope the quiet of the night is treating you well. In our last session, we traveled the long, winding roads of the circulatory loops. We followed the blood as it rushed from the heart to the lungs to catch its breath, and then out to the furthest reaches of the body to deliver its cargo. We saw the heart as a mechanical pump, a physical engine of muscle and valves pushing fluid through a closed system. But tonight, we must address a mystery that lies at the very center of this activity. We know the heart beats. We know the muscle contracts. But what tells it to contract? What is the invisible hand that flips the switch 70 times a minute, every minute, for an entire lifetime? If you were to look at the skeletal muscles in your arm or leg, you would find that they are servants of the brain. They wait. They do not move until a nerve signal comes down from your conscious mind commanding them to lift or step. If you cut the nerve, the muscle is paralyzed. It falls silent. The heart is different. It possesses a quality we call autorhythmicity. This is a beautiful word that literally means self-rhythm. If you were to disconnect all the nerves leading to the heart, or even if you were to remove a heart from the body entirely, as surgeons do during a transplant, it would continue to beat. It does not need the brain to tell it to beat. It only needs the brain to tell it to speed up or slow down. The rhythm itself comes from within. Tonight, we are going to explore the source of this independence. We are going to look at the wiring of the house. We are moving from the mechanical to the electrical. This is the study of the cardiac conduction system, the internal power grid that generates the spark of life. So, let your own heart rate settle. Feel the steady thump in your chest, not as a mechanical thud, but as a wave of energy. Close your eyes, and let us trace the path of the lightning that lives inside you. To understand this system, we must visualize the heart not just as red meat, but as a conductive lattice. Imagine a network of specialized cells that are not quite muscle and not quite nerve. They are a hybrid. They are designed for one purpose: to carry an electrical signal at high speed, coordinating the millions of muscle cells so that they contract in perfect unison. The journey of the heartbeat begins in the upper right chamber. High in the wall of the right atrium, just below where the great superior vena cava enters, sits a tiny cluster of these specialized cells. This cluster is called the sinoatrial node, or the SA node. You have likely heard of it by its common title, the pacemaker. The SA node is the conductor of the orchestra. It is the drummer that sets the beat. These cells are unique because they are unstable. They cannot sit still electrically. Their membranes slowly leak ions until they reach a tipping point, and then snap, they fire off an electrical impulse. This happens spontaneously, roughly 75 times per minute. When the SA node fires, the spark doesn't just stay there, it spreads. Imagine throwing a stone into a still pond. The ripples move outward in perfect concentric circles. In the heart, this ripple is a wave of depolarization. It sweeps across the walls of both the right and left atria. As this electrical wave hits the muscle cells of the atria, it commands them to contract. The top of the heart squeezes, blood is pushed down through the open valves and into the ventricles. But here we encounter a problem. If that electrical signal were to travel straight down to the ventricles immediately, the whole heart would contract at once. The top and bottom would squeeze together, fighting each other, and blood would have nowhere to go. We need a delay. We need the bottom chambers to wait until the top chambers are finished. Enter the second player in our system, the atrioventricular node, or AV node. The AV node sits at the very bottom of the right atrium, near the center of the heart. Think of the AV node as a gatekeeper. It is a relay station. When the signal from the SA node arrives here, something remarkable happens. The signal slows down. The cells in the AV node are thinner and have fewer connections. The electricity hits traffic. It takes about 1/10 of a second for the signal to wade through this node. This pause is intentional. It is critical. During this brief moment of silence, the atria finish their contraction. They squeeze the last drop of blood into the ventricles. The ventricles fill completely. The pause ensures that the priming phase is done before the pumping phase begins. It is the silence before the storm. Once the signal finally makes it through the AV node, it picks up speed again. It shoots into a structure called the atrioventricular bundle, often called the bundle of His, named after the Swiss cardiologist Wilhelm His. This bundle is a cable that runs down the wall between the ventricles. It splits into a right bundle branch and a left bundle branch, running like express highways down to the very tip, or apex, of the heart. Finally, at the bottom of the heart, these branches fray out into thousands of microscopic fibers called Purkinje fibers. These fibers curve upward into the thick walls of the ventricles. The Purkinje fibers are the detonators. They deliver the electrical command to the massive muscle of the ventricles. And notice the direction. The signal travels all the way to the bottom before it spreads to the walls. This means the ventricles begin to contract from the bottom up. Think of a tube of toothpaste. If you want to get the toothpaste out, you don't squeeze the top. You squeeze the bottom and roll upward. The heart does the same. By contracting from the apex upward toward the base, it pushes the blood up and out of the exit doors, the pulmonary and aortic valves, which are located at the top of the ventricles. So, the sequence is SA node, the spark, atria, the spread, AV node, the pause, bundle of His, the highway, Purkinje fibers, the squeeze. Now that we have the roadmap, let us go deeper into the nature of this electricity. When we speak of electricity in a house, we are talking about electrons flowing through a copper wire. But in the body, electricity is the movement of ions, charged particles floating in water. It is a wet electricity. The three main dancers in this ballet are sodium, potassium, and calcium. Imagine a single cell in the SA node. Outside the cell, there is a sea of sodium. Inside the cell, there is a pool of potassium. Nature wants to balance these out. Sodium wants in, potassium wants out. In a normal muscle cell, the doors are locked until a nerve tells them to open. But in the pacemaker cells of the SA node, the doors are leaky. Sodium slowly trickles in, constantly changing the electrical charge inside the cell. It drifts upward, closer and closer to a threshold. This slow drift is called the pacemaker potential. It is a state of perpetual anticipation. The cell is never truly at rest. It is always preparing for the next beat. When the threshold is reached, the gates fly open. Calcium rushes in. This sudden influx of positive charge is the spark or the action potential. Then, potassium rushes out to reset the cell, bringing the charge back down, and the cycle begins again immediately. Drift, fire, reset. Drift, fire, reset. This reliance on ions explains why your doctor checks your electrolyte levels. If your potassium is too high or your calcium is too low, the rhythm changes. The chemical soup must be perfectly seasoned for the spark to ignite on time. But what happens if the conductor falls asleep? What if the SA node fails? The heart is built with incredible redundancy. It has backup systems. If the SA node stops firing, the heart does not stop. The AV node notices the silence. After a moment, it steps up and begins to generate its own rhythm. The AV node is slower, it naturally beats at about 40 to 60 times per minute, but it is enough to keep you alive. It is a reliable understudy. And what if both the SA node and the AV node fail? The cells in the bundle branches and Purkinje fibers can actually try to pace the heart themselves. They are very slow, perhaps only 20 to 40 beats per minute, and not very efficient, but they will try to maintain a rhythm to the very end. This hierarchy of pacemakers is a survival mechanism, a testament to the biological imperative to keep the blood moving at all costs. We must also appreciate the insulation of the heart. I mentioned in the anatomy lesson that the heart has a fibrous skeleton. This dense connective tissue separates the atria from the ventricles. Why is this important electrically? It acts as an insulator, like the rubber coating on a wire. It prevents the electricity in the atria from jumping directly to the ventricles. It forces the signal to go through the only open door, the AV node. This structural barrier is the only reason the critical pause works. Without this insulation, the heart would contract chaotically, and the coordinated rhythm of life would collapse. Take a moment to let that idea find its place. Visualize the heart not just as muscle, but as a house with insulated walls, guiding the light through specific hallways, ensuring that order is maintained over chaos. How do we see this invisible electricity in the real world? You have likely seen it on a screen in a hospital or a movie. The jagged green line beeping across the monitor. That is an electrocardiogram, also known as an ECG or EKG. The EKG is not measuring the movement of the muscle, it is measuring the movement of the electricity. We are literally watching the ions dance. Let's demystify that jagged line. A single heartbeat on the screen has 3 distinct waves. First, there is a small bump called the P wave. This represents the signal firing from the SA node and spreading across the atria. When you see the P wave, you know the top of the heart has just received the command to squeeze. Then, there is a brief flat line. This is the pause. This is the signal waiting at the AV node. Next, there is a massive, sharp spike that goes up and down. This is the QRS complex. It is huge because the ventricles are huge. This represents the signal shooting down the bundle of His and blasting through the Purkinje fibers. It is the electrical roar of the main engines firing. Finally, there is a medium-sized bump at the end called the T wave. This is the recovery. It represents the ventricles resetting their ions, recharging their batteries, and getting ready for the next beat. P, Q, R, S, T, atria, ventricles, reset. When a doctor looks at an EKG, they are looking for the timing between these waves. If the gap between the P and the QRS is too long, they know the signal is getting stuck in the AV node, a condition called heart block. If the QRS is wide and weird, They know the signal is taking a detour through the ventricles. This electrical system is also what we manipulate with technology. If a person's SA node wears out and becomes too slow, we implant an artificial pacemaker. This is a small device with a battery and a wire that threads into the heart. It delivers a tiny, rhythmic shock, replacing the natural spark of the SA node. We have learned to mimic the body's own lightning to extend life. We can also understand the sensation of a skipped beat. Have you ever felt your heart flutter in your chest? Often, this is what we call a premature ventricular contraction, or PVC. This happens when a rogue cell in the ventricle gets impatient. It decides not to wait for the signal from the SA node. It fires on its own, causing an early, weak beat. The heart then pauses for a split second to reset itself before the next normal beat comes crashing in. That heavy thump you feel is not the skipped beat. It is the strong, normal beat that follows the pause. It is the system correcting itself, stumbling for a moment, and then finding its rhythm again. This is a good place to rest your thoughts for a moment before we continue. Let the image of the EKG line smooth out in your mind. Just a steady, rhythmic pulse. The P, the QRS, the T. A language of waves that spells out life, life, life. We have now traced the spark. We understand the who and the how of the signal. We know that the SA node whispers to the atria, the AV node holds the gate, and the Purkinje fibers shout to the ventricles. We have mapped the wiring. But electricity is only the means to an end. The signal is just a command. The result of that command is movement. The spark leads to the squeeze. When the muscle contracts, it changes the space inside the chambers. When the space changes, the pressure changes. And when the pressure changes, the blood moves. This dance of pressure and volume, of squeezing and relaxing, is called the cardiac cycle. It is the mechanical translation of the electrical story we just told. So, having grasped the lightning, we are perfectly prepared to study the thunder. Let's hold that thought here. The image of the glowing conduction network. Our next lesson will connect the wires to the gears, showing us exactly how a heartbeat pumps the fluid. For now, release the need to understand the ions. Let them drift back into their balance. Trust that your own SA node is watching over you, keeping the time while you drift into sleep. Lesson 7. The Cardiac Cycle. Welcome back. I am honored that you have chosen to continue this journey with me tonight. Let yourself settle into the comfort of your surroundings. Feel the support of the surface beneath you, and allow your body to become heavy and soft. There is nothing else you need to do right now. The world outside has paused, giving us this quiet space to turn our gaze inward once again. In our last session, we spoke of the invisible spark. We traced the path of the electrical signal as it raced from the sinoatrial node, across the atria, paused at the gate, and then surged down into the ventricles. We mapped the lightning that lives within the walls of your heart. But electricity, for all its speed and wonder, is merely a messenger. It is the command, not the action. The signal says go, but the muscle must still do the work. Tonight, we are going to witness that work. We are going to watch the lightning turn into thunder. We are entering the study of the cardiac cycle. This term refers to all the mechanical events that occur during a single heartbeat. It includes the contraction and the relaxation, the rising and falling pressures, the opening and closing of valves, and the movement of blood from one chamber to the next. It is a cycle that takes less than 1 second to complete, roughly 0.8 seconds in a resting heart. Yet, within that blink of an eye, a complex ballet of physics takes place. It is a dance of pressure and volume, a rhythmic squeezing and filling that ensures the river of life never runs dry. Tonight, we will slow this cycle down. We will stretch that single second into minutes, allowing us to walk through each phase in slow motion. We will feel the tension build and release. We will understand exactly what is happening in your chest at this very moment. So, take a deep, slow breath, filling your lungs and then emptying them, and let us synchronize our minds with the rhythm of the heart. To understand the cardiac cycle, we must first master two simple concepts: systole and diastole. These are terms you may have heard in a doctor's office, but let us strip away the medical jargon and look at what they physically mean. Systole comes from the Greek word for contraction or drawing together. When a heart chamber is in systole, it is squeezing. The muscle fibers shorten, the space inside the chamber gets smaller, and the pressure shoots up. This is the pumping phase. Think of squeezing a water balloon. You are applying systole to it. Diastole comes from the Greek for dilation or separation. When a heart chamber is in diastole, it is relaxing. The muscle fibers lengthen, the space inside the chamber expands, and the pressure drops. This is the filling phase. Think of releasing your grip on that water balloon and letting it refill from a tap. The cardiac cycle is simply the alternation between these two states. The heart does not squeeze all at once. If it did, blood would have nowhere to go. Instead, the atria and ventricles take turns. Let us walk through the cycle, starting from a moment of total peace. Phase 1. Ventricular filling, mid to late diastole. Imagine the heart is resting. The atria and the ventricles are both relaxed in diastole. Blood is returning from the body and lungs, flowing passively into the atria. Because the pressure in the relaxed ventricles is low, the inlet doors, the tricuspid and mitral valves are hanging open. Gravity and momentum carry the blood straight through the atria and down into the ventricles. It pours in like water into a pitcher. In fact, about 80% of ventricular filling happens just like this, passively, without the heart doing any work at all. Then, the electrical signal fires from the SA node. The atria contract, atrial systole. This is the atrial kick. It squeezes the final 20% of blood down into the ventricles. It is a topping off maneuver, ensuring the pitcher is brim full. Phase 2 is a volumetric contraction, ventricular systole, begins. Now, the focus shifts downstairs. The electrical signal hits the ventricles. They begin to contract. This is a critical, split-second moment. As the ventricle walls squeeze, the pressure inside rises instantly. This sudden spike in pressure forces the inlet valves, tricuspid and mitral, to slam shut. This is the lub sound of your heartbeat. But here is the catch. The exit doors, pulmonary and aortic valves, are still closed. They are held shut by the high pressure of the blood waiting in the arteries. So, for a tiny fraction of a second, the ventricle is a sealed room. All 4 doors are closed. The muscle is squeezing, the pressure is skyrocketing, but the blood has nowhere to go. The volume of blood remains the same. This is why we call it isovolumetric, same volume, contraction. It is like a runner in the starting blocks, muscles tensed, energy building, waiting for the gun. Phase 3, ventricular ejection. The pressure in the ventricle continues to rise until it finally exceeds the pressure in the arteries. Pop. The exit doors, the semilunar valves, are forced open. Blood blasts out. It rushes into the aorta and the pulmonary trunk with tremendous force. This is the payload being delivered. The ventricles don't empty completely, they always keep a little reserve, but they eject the majority of their contents into the system. Phase 4. Isovolumetric relaxation. Early diastole. The contraction ends. The ventricles relax. As the muscle stops squeezing, the pressure inside drops rapidly. The blood that was just pushed into the arteries tries to fall back down, attracted by the sudden low pressure, but as it flows backward, it catches the pockets of the semilunar valves, snapping them shut. This is the dub sound. Once again, for a brief moment, All four doors are closed. The inlet valves haven't opened yet, and the exit valves just closed. The ventricle is a sealed, relaxing room. The tension fades. The pressure falls further until it is lower than the atria, and the inlet valves drift open again. The cycle is complete. We are back to phase 1. Filling begins anew. Now that we have the sequence fill, squeeze, eject, relax, let us layer in some nuance. The beauty of this cycle is in the physics of fluids. Fluids always move from high pressure to low pressure. The heart is simply a machine that manipulates these pressure gradients. Let's focus on the atrial kick. We mentioned that it provides the last 20% of filling. For a young, healthy person sitting quietly, like you are now, this kick isn't strictly necessary. Your ventricles would fill enough by gravity alone to keep you alive. However, during exercise, when the heart is beating fast, the time for passive filling is cut short. That is when the atrial kick becomes vital. It ensures the ventricles get enough blood to pump effectively even at high speeds. This explains why a condition like atrial fibrillation, where the atria quiver instead of contracting, is survivable, but leaves a person feeling tired and winded. They have lost their kick. They have lost their turbocharger. We should also define two key volumes that cardiologists measure. First, the end diastolic volume, EDV. This is the amount of blood in the ventricle at the very end of filling, just before it pumps. Think of this as the full tank amount. It's usually about 120 to 130 milliliters. Second, the end systolic volume, ESV. This is the amount of blood left over in the ventricle after it has pumped. Remember, the heart never empties completely. It is not like squeezing a lemon dry. It is more like squeezing a sponge. There is always some fluid left. This reserve is usually about 50 to 60 milliliters. The difference between these two numbers is the stroke volume. Full tank minus reserve equals amount ejected. Normally, the heart pumps out about 70 milliliters of blood with each beat. This little cupful of blood is the stroke that sustains your life. There is another fascinating detail in the pressure curve called the dicrotic notch. Imagine the moment the aortic valve closes. The blood in the aorta tries to flow back, slams the door shut, and bounces off the valve. This bounce creates a tiny, momentary spike in pressure in the artery. Why does this matter? It shows us that the arteries are elastic. They are not rigid pipes. When the heart pumps, the arteries stretch to accept the blood. When the heart relaxes, the arteries recoil, squeezing the blood forward. This recoil effect keeps the blood flowing smoothly, even when the heart is resting. It turns a pulsed flow, start, into a continuous flow. The heart pushes, then the artery pushes. They work as partners. Take a moment to let that idea find its place. Visualize the artery as a second heart, a gentle echo of the first. The main heart beats, and the artery responds with a soft squeeze of its own, guiding the blood further down the road. How does this mechanical cycle translate to the numbers you see at the doctor's office? Let's talk about blood pressure. When the nurse wraps the cuff around your arm and announces 120/80, they are giving you a direct status report on your cardiac cycle. The top number, 120, is the systolic pressure. This measures the peak pressure in your arteries when the ventricles are contracting, phase 3. It is the force of the wave crashing against the vessel walls. It tells us how hard your heart is working. The bottom number, 80, is the diastolic pressure. This measures the pressure in your arteries when the heart is resting and refilling. Phase 1 and 4. It is the baseline pressure in the system. If the bottom number is too high, it means your arteries are under stress even when the heart is relaxing. The system never gets a true rest. This is why high diastolic pressure is a concern. It is like a tire that is overinflated even when the car is parked. Let's also return to the sounds lub-dub. We now know that lub is the closing of the inlet valves, AV valves, at the start of systole. We know that dub is the closing of the exit valves, semilunar valves, at the start of diastole. But notice the silence. Between lub and dub, there is a short silence. This is systole, the squeeze. Between dub and the next lub, there is a longer silence. This is diastole, the rest. Normally, the rest is longer than the work. The heart spends more time relaxing than it does pumping. In a standard cycle, systole is 0.3 seconds and diastole is 0.5 seconds. This is a profound realization. Your heart, the hardest working muscle in your body, actually sleeps more than it works. It takes micro naps between every single beat. It is this balance, this built-in rest period, that allows it to function for 80, 90, or 100 years without fatigue. If your mind is still following along, try visualizing this. Imagine a rower on a lake. The stroke of the oar is strong and fast, systole. But the glide across the water, where the oars rest and the boat drifts, is long and smooth, diastole. Your life is sustained not just by the stroke, but by the glide. The rest is as important as the effort. We have now watched the engine run. We have seen the chambers fill, the pressure build in the sealed room, the valves pop open, and the payload launch. We have heard the doors slam shut and felt the peace of the refilling phase. We understand the cycle of the pump, but once the blood leaves the heart, it enters a new world. It enters the maze of the vasculature. We have mentioned arteries and veins before, but they are not just passive tubes. They are dynamic, living structures with their own anatomy and their own rules. Some vessels are thick and elastic, others are thin and leaky. Some have valves, others do not. To understand how the blood actually reaches the cells, we must examine the highways it travels on. So, having understood the heartbeat, we are perfectly prepared to understand the vessels. Let's hold that thought here. The rhythmic expansion and contraction of the cycle. Our next lesson will take us out of the heart and into the arteries, veins, and capillaries. For now, simply rest in the long, quiet glide of your own diastole. Lesson 8. Blood vessel structure and function. Welcome back. I hope you are finding a deep sense of peace as we continue our nightly study. In our previous sessions, we have spent a great deal of time in the engine room. We have explored the heart in all its complexity, its chambers, its valves, its electrical spark, and the rhythmic cycle of its beat. We have witnessed the force that launches the journey, but a launch is only the beginning. Once the blood leaves the sanctuary of the heart, it enters the vast, sprawling wilderness of the body. It enters the network of the vasculature. Tonight, we are going to leave the central station and travel down the tracks. We are going to explore the blood vessels. It is easy to think of these vessels as simple, passive tubes, just rubber hoses carrying water from point A to point B. But as we will discover tonight, they are dynamic, living organs in their own right. They are capable of changing their size, their shape, and their function from moment to moment. They are intelligent highways that direct traffic exactly where it is needed most. We will learn to distinguish the three great families of vessels: the high-pressure arteries, the low-pressure veins, and the microscopic marketplaces known as capillaries. We will examine the walls of these tunnels and see how their architecture perfectly matches their specific jobs. So, let your imagination expand. Picture a map of a great country with massive interstates, winding country roads, and tiny footpaths. Now, fold that map up and place it gently within your own chest. You are that country. Let us explore your roads. To understand the vascular system, we must first establish a golden rule of direction. In anatomy, the names of the vessels are determined not by what they carry, but by where they are going. Arteries are the vessels that carry blood away from the heart. Think of the letter A, artery, away. Veins are the vessels that carry blood back toward the heart. Think of the visit return trip. Capillaries are the tiny bridges that connect the two. Let us begin with the arteries. Imagine standing inside the aorta, the largest artery in the body, just outside the exit door of the left ventricle. The environment here is violent. Every time the heart beats, a shockwave of high-pressure fluid slams into these walls. To survive this, arteries are built to be tough. If you were to touch the wall of a healthy artery, it would feel thick and rubbery. It is designed to stretch. When the heart pumps, the artery expands to accept the blood, like a balloon inflating. When the heart relaxes, the artery snaps back, squeezing the blood forward. This elasticity is crucial. It turns the intermittent spurt of the heart into a smoother, continuous flow. As the arteries travel further from the heart, they branch like a tree. The massive trunk of the aorta splits into large branches, which split into smaller branches, eventually becoming tiny arterioles. These arterioles are the control valves of the system. They have a lot of muscle in their walls. By squeezing tight or opening wide, they determine which neighborhoods get blood and which do not. The road eventually ends at the capillaries. We have arrived at the destination. The capillaries are the smallest vessels in the body, so narrow that red blood cells often have to fold in half just to squeeze through, marching single file. While arteries and veins are just transport tubes, the capillaries are the functional part of the system. This is where the actual business of keeping you alive happens. The walls of a capillary are incredibly thin, only one single cell thick. This thinness allows oxygen, nutrients, and water to slip right through the wall and feed your tissues. Simultaneously, waste products like carbon dioxide slip from the tissues back into the blood. It is a busy, silent marketplace of exchange. Once the blood has passed through the capillaries and done its job, it enters the venules, which are small veins. These merge together to form larger and larger veins. The environment in the veins is very different from the arteries. The pressure here is low. The violent push of the heart has been lost in the friction of the capillaries. The river is now slow and lazy. Because they don't have to withstand high pressure, the walls of veins are much thinner and floppier than arteries. If an artery is a stiff rubber hose, a vein is a soft, collapsible sleeve. But this low pressure creates a problem. How does the blood get back to the heart, especially from your feet, fighting against gravity? The veins have a secret weapon: valves. Inside the veins of your arms and legs are tiny flaps of tissue. They work like rungs on a ladder. The blood pushes up past a valve, and then, if it tries to slide back down, the valve catches it. Step by step, the blood climbs the ladder back to the heart. Now that we have the general layout, let us look closer at the construction materials. If we were to slice a blood vessel open and look at it under a microscope, we would see that the walls are built in layers, or tunics. Just as you might wear a shirt, a sweater, and a coat, vessels wear three distinct tunics. The innermost layer, the one that touches the blood, is the tunica intima. This is the same smooth, slick endothelium we saw inside the heart. Its job is to provide a friction-free surface. It must be as smooth as glass so the blood cells can glide without snagging or clotting. The middle layer is the tunica media. This is the layer of muscle and elastic tissue. In arteries, this layer is very thick. It is the muscle here that contracts to raise your blood pressure or relaxes to lower it. This layer is controlled by the sympathetic nervous system, the unconscious part of your brain that manages your fight or flight responses. In veins, This muscle layer is much thinner, as they don't need to regulate pressure in the same way. The outermost layer is the tunica externa. This is a tough jacket of collagen fibers. Its job is to protect the vessel and anchor it to the surrounding tissues, so it doesn't move around too much. Interestingly, in the very largest vessels like the aorta, this outer wall is so thick that it needs its own blood supply. It has tiny blood vessels on the blood vessel. We call these the vasa vasorum, literally, vessels of the vessels. Let us spend a moment appreciating the capillary beds. We often think of capillaries as always being open, but that isn't true. You have so many capillaries in your body that if they were all open at the same time, your blood pressure would drop to 0 and you would faint. There simply isn't enough blood to fill every street in the city at once. So, the body prioritizes. At the entrance to each capillary bed is a tiny ring of muscle called a precapillary sphincter. It acts like a toll booth. Imagine you are eating a large meal. Your stomach needs energy to digest. The sphincters leading to your digestive system open wide, flooding the stomach with blood. At the same time, the sphincters leading to your leg muscles might close down slightly, diverting traffic to where the work is happening. Conversely, if you are running a race, the stomach closes shop and the floodgates to the legs open wide. This is a constant, shifting dance of resources. This mechanism is called shunting. Your body is constantly shunting blood from one area to another, chasing the demand. Even now, as you sleep, blood is being shunted away from your muscles and toward your skin to release heat, or toward your brain to facilitate dreaming. We must also discuss the challenge of venous return. We mentioned the valves in the veins, but valves alone are not enough to pump blood up from the toes. The veins need help. They get it from two external pumps. The first is the skeletal muscle pump. The deep veins of your legs are buried inside the calf muscles. Every time you take a step, the muscle bulges and squeezes the vein. This squeeze pushes the blood up. This is why walking makes you feel better. You are literally pumping your own blood with your legs. It is also why standing still for a long time can make you faint without the muscle movement. The blood pools in your feet, and the brain gets deprived. The second helper is the respiratory pump. Every time you inhale, your diaphragm moves down. This increases pressure in your abdomen and decreases pressure in your chest. This pressure difference acts like a vacuum, sucking blood up from the belly and into the chest toward the heart. Every breath you take pulls the venous blood home. Take a moment to let that idea find its place. Visualize your breath as a tide, in and out. With every inhalation, you are drawing the river upward. With every step you take in the daylight, you are assisting your heart. You are a system of collaboration. How does this structural knowledge manifest in our daily medical experiences? Consider the simple act of a blood draw. When a nurse needs to take a blood sample, they almost always choose a vein, usually the one in the crook of your elbow. Why not an artery? The anatomy gives us the answer. First, arteries are deep, protected by muscle and bone because they are vital high-pressure lines. Veins are superficial, often visible right under the skin. Second, arteries have thick walls that are hard to puncture, while veins have thin walls that are easy to access. But most importantly, it is about pressure. If you puncture an artery, the blood is under such high pressure that it would spray out and be difficult to stop. Puncturing a vein is safer. The low pressure means the blood flows out gently, and the leak is easily sealed with a small cotton ball. We work with the anatomy, not against it. We can also understand the condition known as varicose veins. Remember the ladder of valves in the leg veins? Sometimes, due to genetics, pregnancy, or standing for many years, the walls of the veins stretch. When the vein stretches, it becomes too wide. The valve flaps can no longer meet in the middle. The seal is broken. Blood that should be climbing up leaks back down. It pools in the lower legs, causing the veins to swell, twist, and bulge. The purple, winding lines you see on a leg are simply veins that have lost their structural integrity ladders with broken rungs. Consider also the phenomenon of atherosclerosis, or hardening of the arteries. Healthy arteries are elastic. They expand and recoil. But if plaque builds up in the walls, the artery becomes rigid. It turns from a rubber hose into a lead pipe. Now, when the heart pumps, the artery cannot stretch to absorb the shock. The pressure spikes higher. The heart has to work harder to push against this stiff resistance. Over years, this extra work thickens the heart muscle and wears it out. This is why maintaining the health of the pipes is just as important as maintaining the health of the pump. Finally, think about blushing. When you are embarrassed or hot, your face turns red. This is the tunica media in the arterioles of your skin relaxing. The vessels dilate, bringing warm, red blood to the surface to release heat. When you are frightened or cold, you go pale. The muscle contracts, clamping the vessels shut, keeping the blood deep inside to protect your core. Your skin color is a direct reflection of the opening and closing of these microscopic gates. This is a good place to rest your thoughts for a moment before we continue. Let the complexity of the network fade. Simply feel the warmth in your hands and feet. That warmth is the blood arriving. It is the successful navigation of the maze, delivered silently to every inch of you. We have now mapped the highways. We know the difference between the thick, pulsing arteries and the soft, valved veins. We have stood in the marketplace of the capillaries where life is exchanged. We see the vessel walls not as dead tubes, but as living, reacting tissues. But knowing the structure of the pipes is only half the battle. To truly understand how this system keeps you alive, we must understand the physics that govern the fluid inside them. Why does blood flow? What stops it? What makes the pressure rise or fall? There is a relationship between the pump, the resistance of the pipes, and the volume of the fluid. It is a mathematical dance called hemodynamics. Having grasped the anatomy of the vessels, we are perfectly prepared to study the forces that act within them. So, let's hold that thought here. The image of the vast vascular tree. Our next lesson will explain the rules of the road, exploring blood pressure and the physics of flow. For now, let the image of the winding river carry you further into relaxation, knowing that the flow within you is steady and sure. Lesson 9. Hemodynamics and blood pressure. Welcome back. I am glad you have returned to our nightly sanctuary. Take a moment to adjust your position, perhaps easing the tension in your shoulders or softening the muscles of your face. Let the external world fade, leaving only the quiet space of our shared inquiry. Throughout this series, we have constructed a magnificent machine in our minds. We have built the pump, the heart, laid down the pipes, the blood vessels, and analyzed the fluid, the blood, that travels through them. We have seen the anatomy, the physical structures that you could touch and hold. But anatomy is only the stage. Physiology is the play. Tonight, we move from the static structures to the dynamic forces that govern them. We are entering the realm of hemodynamics. Hemo means blood. Dynamics means power or force. This is the study of the physics of blood flow. It is the answer to the question, why does blood move? How does the body ensure that a red blood cell traveling to your brain gets there against gravity? How does it ensure that the pressure is high enough to feed the kidney, but not so high that it bursts the delicate capillaries? It ultimately boils down to a delicate dance between three variables: flow, pressure, and resistance. Tonight, we will unravel the relationship between these three. We will demystify what blood pressure actually is, beyond just numbers on a screen. We will see how your body constantly tweaks the diameter of your vessels, playing a symphony of physics to keep you alive. So, breathe deeply and let us step into the flow. To understand hemodynamics, we do not need complex calculus. We simply need to visualize a garden hose. Imagine you are watering a garden. You turn on the tap and water flows out the end of the hose. The amount of water coming out is the flow. The force of the water pushing against the walls of the hose is the pressure. And anything that slows the water down, like a kink in the hose, or dirt inside it, or just the friction of the rubber, is the resistance. There is a simple, beautiful rule that governs this, often called Ohm's law for fluid. Flow equals pressure divided by resistance. What does this mean for you? It means that for blood to flow, there must be a pressure difference. Blood, like water, will only move from a place of high pressure to a place of low pressure. It is the heart's job to create that high pressure at the start of the line. But the most critical player in this equation is often the resistance. Resistance is the enemy of flow. If resistance goes up, imagine squeezing the hose. Flow goes down unless you increase the pressure to compensate. In the human body, the resistance comes mainly from three things. First, viscosity. We touched on this in lesson 2. Thicker fluid is harder to push. Honey flows slower than water. If you are dehydrated, your blood is thicker, resistance is higher, and your heart works harder. Second, vessel length. The longer the hose, the more friction there is. Every pound of fat you gain adds miles of new capillaries to your body. That extra length adds resistance, which again forces the heart to work harder. But the third factor is the most important because it can change in an instant: vessel diameter. This is the master key. If a blood vessel gets wider, called vasodilation, resistance drops dramatically and blood flows easily. If a vessel gets narrower, called vasoconstriction, resistance skyrockets, and it becomes very hard to push blood through. Think of drinking a milkshake. If you use a tiny, narrow straw, high resistance, you have to suck very hard, high pressure, to get any shake, flow. If you switch to a wide, thick straw, low resistance, the shake flows easily with little effort. Your body is constantly switching straws, thousands of times a day, adjusting the width of your arterioles to manage the pressure and flow. Now, let us apply this physics to the term we all know: blood pressure. When a doctor wraps that cuff around your arm, what are they measuring? They are measuring the force exerted by the blood against the wall of the artery. It is the tension in the hose. We record it as two numbers, like 120/80. The top number, systolic pressure, is the peak pressure. This happens when the left ventricle contracts. It is the crest of the wave crashing through your arteries. The bottom number, diastolic pressure, is the baseline pressure. This happens when the heart is resting between beats. You might ask, why is there still pressure when the heart is resting? Shouldn't it drop to zero? This is where the genius of your arteries comes in. Remember the elastic recoil we discussed? Your arteries are elastic, like a rubber band. When the heart pumps, the arteries stretch out. This stores energy. When the heart stops pumping during diastole, the arteries snap back. This snapback keeps squeezing the blood forward even while the heart is filling. It turns the heart's stop and go, pumping into a relatively smooth flow. If your arteries were rigid pipes like metal plumbing, your blood pressure would be 120 when the heart beat and 0 when it rested. The flow would stop completely between beats. You would faint every time your heart paused. The elasticity of your vessels maintains that diastolic pressure, the 80, to keep the blood moving constantly. Now, consider the concept of pulse pressure. This is simply the difference between the top and bottom numbers. 120 minus 80 equals 40. This represents the throb you feel at your wrist. As we age, Our arteries lose their elasticity. They become stiff, a condition called arteriosclerosis. They can't stretch as well, so the systolic pressure shoots up higher because the pipe won't give, and the diastolic pressure drops lower because there is no snapback. The pulse pressure gets wider. A wide pulse pressure is often a sign of aging arteries. Let's also talk about the pressure drop. In the aorta, pressure is high, about 120 mmHg. By the time blood reaches the capillaries, pressure has dropped to about 35 mmHg. Why the drop? Because the capillaries are fragile. If 120 mmHg of pressure hit a capillary, it would explode. The resistance of the arterioles acts like a pressure dam, slowing the river down and protecting the delicate destination. And by the time the blood reaches the veins and gets back to the right atrium of the heart, the pressure is almost zero. The blood barely trickles home. This is why, as we learned, we need valves and muscular pumps to help the veins return the blood. Take a moment to let that idea find its place. Visualize a rushing mountain waterfall, the arteries, slowing down into a calm, winding stream, the capillaries, and finally entering a deep, slow lake, the veins. The water is the same, but the energy changes. How does this physics lesson apply to your life and health? It explains the logic of hypertension or high blood pressure. Hypertension is often called the silent killer because you can't feel it, but mechanically it is devastating. If your vessels are constricted or stiff, high resistance, your heart must pump harder to maintain flow. Imagine trying to blow up a balloon that is too stiff. You have to strain. Over time, this strain causes the heart muscle to thicken, a condition called hypertrophy. At first, this sounds good. Muscle is good, right? But a thick heart is a stiff heart. It can't fill properly. Eventually, it wears out and fails. Furthermore, high pressure damages the walls of the vessels themselves. It creates microscopic tears in the inner lining. Your body tries to patch these tears with cholesterol and scar tissue. This is how plaque forms. So, high blood pressure leads to plaque, which narrows the vessel further, which raises blood pressure even more. It is a vicious cycle. This understanding of resistance also explains how stress affects you. When you are stressed, your body releases adrenaline. Adrenaline is a powerful vasoconstrictor. It tells the muscles in your artery walls to tighten. Why? Because evolutionarily, stress meant a tiger was chasing you. Tightening the vessels, increasing pressure, helped blast blood to your muscles for a sprint. But today, the tiger is a traffic jam or a deadline. You sit still, but your vessels tighten. Your pressure spikes, but you don't run. The energy has nowhere to go but against your own arterial walls. On a lighter note, this physics also explains why you feel dizzy if you stand up too fast, a phenomenon called orthostatic hypotension. When you are lying down, like now, your heart doesn't have to work hard against gravity. Pressure is equalized. When you stand up suddenly, gravity pulls the blood down into your legs. For a split second, there isn't enough pressure to push blood up to your brain. You see stars. Normally your body fixes this in seconds by constricting the leg vessels, increasing resistance to push blood back up. It is a momentary lag in the hemodynamics of your system. If your mind is still following along, try visualizing this. Think of the thermostat in your house. It constantly adjusts the heat to keep the temperature stable. Your body has a pressure stat. It constantly adjusts the diameter of your vessels to keep the pressure stable. You are a self-regulating machine. We have now defined the forces. We understand that flow is the goal, pressure is the push, and resistance is the obstacle. We understand the delicate interplay between the pump, the pipes, and the fluid thickness. We know that the body is constantly fighting gravity and friction to keep the river moving. But this brings us to the final, critical question. Who is the manager? We know the vessels can constrict, but what tells them to do so? We know the heart can speed up, but what commands it? The system is not chaotic. It is tightly controlled. There is a central command that monitors blood pressure second by second and sends out orders to the heart and vessels to maintain balance. This is the nervous system and the endocrine system working in harmony. Having understood the physics, we are perfectly prepared to meet the manager. So, let's hold that thought here. The image of the pressurized flow. Our final lesson will bring everything together, exploring cardiovascular regulation and integration. For now, simply let your own pressure settle. Let the resistance in your body melt away, leaving only the gentle, unobstructed flow of rest. Lesson 10. Cardiovascular Regulation and Integration. Welcome, traveler. You have arrived at the final destination of our journey. Over the course of these lessons, we have constructed an entire world within your mind. We began with the grand overview, seeing the loop of life that connects every cell. We examined the fluid carrier, the blood, and the miraculous way it seals its own leaks. We walked through the 4 chambers of the heart, listened to the closing of its valves, and watched the electrical spark that sets the rhythm. We traveled down the highways of the arteries and the byways of the veins, and we studied the laws of physics that govern the flow. We have built the machine. We understand its parts. We understand its fuel. But a machine, no matter how complex, cannot run itself without a driver. It cannot adapt to changing road conditions without a navigator. Tonight, in our final lesson, we answer the ultimate question. Who is in control? How does your body know when to speed up the heart? How does it know when to tighten the vessels? How does it maintain that perfect balance, or homeostasis, whether you are sprinting for a bus or lying here in deep, restful sleep? We are going to explore cardiovascular regulation. We will meet the silent conductors, the nerves and hormones that constantly monitor and adjust your internal state. And finally, we will integrate everything we have learned, seeing the cardiovascular system not as a collection of parts, but as a unified, singing whole. So, for this last time, let your body sink into the mattress. Release any final tension you are holding. You do not need to manage your own heartbeat tonight. You do not need to tell your vessels to constrict or dilate. A deep, ancient wisdom within you is handling it all. Let us simply observe it with gratitude. To understand regulation, we must imagine a command center. Deep inside your brain, at the very base of the skull, lies a primitive structure called the brainstem. Within the brainstem is a specific region known as the medulla oblongata. This is the headquarters. Specifically, it houses a cluster of neurons called the cardiovascular center, or CVC. Think of the CVC as the traffic control tower for your entire circulatory system. It is awake 24 hours a day, receiving reports from all over the body and sending out orders in real time. The CVC has 2 primary tools to control the system. These are the 2 branches of the autonomic nervous system. The first tool is the sympathetic nervous system. This is the accelerator. It is the fight or flight system. When the CVC activates this branch, it sends signals down the spinal cord to the heart, telling it to beat faster and harder. It also sends signals to the arteries, telling them to constrict, which raises blood pressure. The second tool is the parasympathetic nervous system. This is the brake. It is the rest and digest system. Its signals travel primarily through the vagus nerve, directly to the heart, telling it to slow down and take it easy. But how does the control center know which tool to use? It needs information. It relies on a network of sensors scattered throughout your body. The most important of these are the baroreceptors. Baro means pressure. These are pressure sensors. They are located in the walls of the carotid arteries in your neck, monitoring blood flow to the brain, and in the arch of the aorta, monitoring flow to the body. Baroreceptors are actually stretch receptors. When blood pressure is high, the artery walls stretch. The baroreceptors feel this stretch and fire rapid signals to the brain. Pressure is high, too high. The brain receives this message and responds instantly. It hits the brake, parasympathetic, to slow the heart and eases off the gas. Sympathetic, to dilate the vessels. The result? Blood pressure drops back to normal. Conversely, if you stand up quickly and blood drains from your head, the pressure drops, the artery walls relax and become less stretched. The baroreceptors stop firing. The brain notices the silence. Pressure is low, too low. It immediately hits the gas. The heart speeds up, the vessels clamp down, and pressure is restored before you even realize anything happened. This is a negative feedback loop. It is a self-correcting cycle that keeps your blood pressure within a safe, narrow range, moment by moment. While the nervous system handles the second-by-second adjustments, there is another layer of control for the long term. This is the endocrine system, or hormonal control. If nerves are like emails, fast and instant hormones are like letters sent through the post slower, but with lasting effects. Let us look at a few key chemical messengers. First, epinephrine and norepinephrine, also known as adrenaline. These are released by the adrenal glands during stress or exercise. They circulate in the blood and act as a booster shot for the sympathetic system, keeping the heart rate and blood pressure elevated for as long as the danger lasts. Then there is the masterful system for managing blood volume, involving the kidneys. It is called the renin-angiotensin-aldosterone system. That is a mouthful, so let's break it down gently. When your kidneys detect that blood pressure is too low, they release an enzyme called renin. Renin sets off a chain reaction in the blood that produces angiotensin II. Angiotensin II is a powerful vasoconstrictor. It tightens the vessels immediately to raise pressure. But it also tells the adrenal cortex to release aldosterone. Aldosterone tells the kidneys to save salt, and where salt goes, water follows. So, the body retains water, increasing blood volume, which raises blood pressure. Finally, there is the antidiuretic hormone ADH. This comes from the pituitary gland in the brain. When you are dehydrated, ADH is released. It tells the kidneys to stop making urine and keep the water in the blood. This conserves volume and maintains pressure. There is also a chemical control based on the quality of the blood, not just the pressure. We have chemoreceptors located near the baroreceptors. They taste the blood. They measure pH, carbon dioxide, and oxygen levels. If carbon dioxide builds up, making the blood acidic, these sensors scream to the brain. The brain responds by speeding up the heart to cycle the blood faster to the lungs, blowing off the excess CO2. This is why your heart races when you hold your breath or exercise hard. The chemistry dictates the mechanics. Let us also integrate the concept of autoregulation. This is a fascinating local phenomenon. Individual organs have the ability to demand more blood without asking the brain for permission. For example, if you are wiggling your toes, the muscles in your toes are using up oxygen and producing waste. This waste causes the local capillaries in the toes to dilate automatically. Blood flows in to clean up the mess. The brain didn't order it. The tissue itself demanded it. It is like a local manager ordering supplies without calling corporate headquarters. Take a moment to let that idea find its place. Visualize the layers of control, the swift electrical signals of the nerves, the slow, drifting clouds of hormones, the local whispers of the tissues. It is a symphony of communication. all singing the same song, survival. How do we see this regulation in our daily lives? Let's look at the white coat effect. Many people have normal blood pressure at home, but when they go to the doctor, it spikes. Why? Anxiety. The anxiety triggers the cerebral cortex, the thinking brain, which sends a message down to the hypothalamus, which activates the sympathetic nervous system. The heart speeds up, vessels constrict, and the reading on the cuff goes high. It is a perfect example of how your thoughts and emotions can override the automatic settings of the cardiovascular system. Conversely, consider the feeling of deep relaxation you are experiencing right now. This is the dominance of the parasympathetic nervous system. Your vagus nerve is currently active. It is secreting a chemical called acetylcholine onto your heart nodes, telling them to slow down. It is quieting the fire. This restorative state is essential for healing. It is during this rest and digest phase that the heart muscle repairs itself, the vessels regain their elasticity, and the system resets for the next day. We can also look at the integrated response to exercise. Imagine you start to jog. Anticipation. Even before you move, your brain sends a signal to increase heart rate. Movement. Your muscles pump, sending venous blood rushing back to the heart. Preload increases. Chemistry. Your muscles produce CO2 and heat. Chemoreceptors detect this and signal the brain to pump harder. Local control. The vessels in your legs dilate to accept the flow, while vessels in your stomach constrict to save energy. Cooling. As body temperature rises, vessels in the skin dilate to radiate heat. You get red. Every lesson we have learned, from the pump mechanics to the vessel physics to the neural control, happens simultaneously in a coordinated dance. It is not separate systems. It is one life. If your mind is still following along, try visualizing this. You are a self-correcting vessel on a vast ocean. When the wind blows, stress, the sails trim themselves. When the current slows, rest, the rudder adjusts. You are never static. You are always in a state of dynamic balance. We have now reached the end of our curriculum. Let us look back one last time at the landscape we have traversed. We started with the introduction, realizing that the cardiovascular system is a closed loop of transport designed to overcome the limitations of distance within the body. We studied the blood, seeing it as a connective tissue of plasma and cells, carrying oxygen and defending against infection. We marveled at hemostasis, the body's ability to seal its own breaches and protect the integrity of the loop. We explored the heart, the four-chambered double pump. We walked through the atria and ventricles, inspected the valves, and understood the difference between the pulmonary and systemic circuits. We watched the conduction system, the internal spark that generates the rhythm of life, independent of the brain. We analyzed the cardiac cycle, the mechanical dance of systole and diastole, pressure and volume, contraction and relaxation. We mapped the vessels, distinguishing the elastic arteries, the valved veins, and the delicate capillaries where the exchange of life occurs. We learned the physics of hemodynamics, seeing how pressure, flow, and resistance interact to keep the river moving. And finally, tonight, we met the regulators, the silent, nervous, and hormonal controllers that maintain homeostasis through every moment of your existence. This system is yours. It belongs to you. It is you. It operates in silence. It asks for no praise, no payment, and no instruction. It simply serves. As you lie here, drifting toward the edge of sleep, realize that you can fully let go. You can resign your post as the captain of the ship for the night. The sensors are active. The pump is strong. Your heart will continue its steady rhythm, slowing down to a gentle, restorative pace. Your vessels will relax, allowing the warmth of the blood to soothe your limbs. Your blood will continue its endless circle, feeding, cleaning, and protecting you while you dream. There is nothing left to learn tonight. There is nothing left to do. The lesson is complete. The system is functioning perfectly. You are safe. You are whole. You are alive. Rest now in the quiet certainty of your own biology. Good night.